Good day, gentle readers. Today is December 12, 2024. Today in Logos 2000, some more of the ideas to continue from the studies and foundations, as what last episode was largely about the theory of color and the theory of light and color, as with regards to our phenomenology and sight as the most evolutionarily developed sense of primates and mammals and lizards and reptiles and many and most kinds of creatures that employ sight. That color is seen to have more going on than the usual accounts. And it begins in primary school with accounts of the theory of additive and subtractive colors and the color wheel, and as with regards to the combinations thereof. And then as well, it gets very, very thoroughly explored by, here from example, Ogden Rood, and what came to be the Community the International Declarage, or the CIE, whose theories and later standards help to define what are these gradations of and the definitions of ranges according to the spaces, the color spaces of what colors additively and subtractively come together, is with regards to mix and blend, arrive at them what each piece in its own region according to its tone exists, hue, saturation, and brightness, intensity, luminosity and chrominance, the colors. The theory of color has a lot going on, and as well it has parts that aren't so much yet explained by the usual regular theory of physics, which is assigned the role of fundamentally having a theory altogether that arrives at that it can be derived, all these things having to do with these matters of perception, which are combined, as was discussed a bit, of the things to do with the not the illusory, but the phenomenological, and as with regards to the optical. So that was kind of the content of the last couple of episodes, was that light and color has a very special role and a very central role in the phenomenological, and so for the theory of physics, and as well that it's separated from electromagnetic radiation. This light is radiation. And it's separated from the kinetic, and with regards to the glowing of the incandescent, these ideas of the fluorescent and the phosphorescent, these different means of the production of the emission of light. And as with regards to all these different things going on with the optical with respect to parallax, and this complementary dual term peripheral parallax, helping to explain why the global vision of a sort has, since the time of the ancient Sumerians, the division of the sky into three realms, and why it is that various matters of scale with regards to the horizon have the effects why they're so, helping to explain why lensing, like gravitational lensing, is a thing, and that during eclipses it's possible to observe these effects going on when the face of the moon in a lunar eclipse rolls over and it exhibits this property, the imaging according to the transit of the syzygy as it is, or why it is so that light always follows all of its paths, and makes for so that why the sun coming around an obstacle, as it were, comes all the way around and fulfills its image even when it's partially blocked, that it's not just gravitational lensing of a sort, that it's as well, that's kind of large Fresnel lensing, it's called here, that it then has the reasons why it can so be, helps to explain also things in the greater survey of things like the redshift bias, and why the inflationary epoch, and this is kind of tuned to a measurement that isn't really accurate in a sort of sense, when it is to be understood how redshift bias arises simply as of a factor of lensing in the free rotational. In these extended discussions here, there's quite a bit of less theory to help arrive at in this greater account why things like a redshift bias can help explain where dark matter, the most of it really lives, and where dark energy, the most of it really lives, is merely is according to the effects in the space of the space-like, the time-like, and the light-like that are the different matters of the basis of projection and perspective in these theories. Physics is fundamentally. Light is established as its own thing, and then it as well has these higher level accounts as after fluorescence and phosphorescence and incandescence, and as with regards to electrical and field and effects, and as with regards to the nuclear fields and effects, and as with regards to the plain optical, the visible light. That it helps a lot to reflect it. Thusly, where it's been kind of overloaded, not just the invisible light or photons that nobody ever sees, the virtual photons put into theories like quantum electrodynamics, is Feynman's placeholder for some kind of particles that are massless and chargeless, yet carry energy about. The invisible photons. Then as well, getting into the issues of the theory of color, then there really is a colorless green in the monochromatic as with regards to luminosity, and there really is a very green. That these are the two kinds of ways to look at it with regards to where then that thusly it can be possible to make a lot of different readily accessible and immediately phenomenological accounts of experiments to just help show that light is superclassical in this way, and superclassical again. One of the talks many hours ago was about the free information, fixed and free information. So the idea of this is kind of arrived and was discussed in Moment and Motion, is that we have a usual model of that information is limited by the speed of light. The idea being that affects to have observers, that it's according to the speed of light that such information can propagate and arrive from point to point. So the idea is that that's part of this free if metered propagation of light. And so when there's actually in a greater space and the kinetic and for general relativity defining the geodesy for this in the same theory, it just has to make it so that for this Lorentzian, Fitzgeraldian, Galilean approach to the linear, and for this free rotating Lorentzian approach for the rotational, as was put forward after reading in Moment and Motion and from reading from Einstein about his second famous mass energy equivalency formula, that is formally unlinear. Is the idea that's helping establish that even in the theory of general relativity and special relativity, as they are just by themselves, that it can be equipped with these models of the linear and rotational as separate, helping make kinetics and kinematics separate, and helping also that when you get into electrical and electromagnetism, that all these things to do with the back and forth in the electromagnetic arrive as natural and kind of courtesy, this exact same account. With regards to the heft and the story of momentum and these kinds of things, and that worlds turn, that it's all the way into classical mechanics and into the premier theories of the day, why it is so that these greater superclassical accounts make for equipping the theory from the foundations with these superclassical accounts, because infinity and continuity are part of physics and reality writ large. And the theories and the very successful theories we have today have taken a great effort and have a long and complicated route to arrive at where it's kind of like, well, for tractability and to understand things about laws of large numbers, that this is the way we have, and it all leads to zero, and it's a law of small numbers is our law of large numbers. That then in the greater space, when you have more than one definition of continuity, and you can make a logical theory that arrives at how that That's not inconsistent, and to be complete inconsistent, it has to be replete in this sense. That these theories of the superclassical and then the modern and postmodern superclassical mathematics of infinities and infinitesimals make for this continuum mechanics, which it is. That it is a continuum mechanics of theory. That these sorts of accounts then make for helping to effect to relay that these kinds of ideas can be given and received and given again, relayed, the ideas of infinity and so on. And there was addressed how, and recently, for example, how like Leibniz says so. And that Husserl and Derrida are trying to figure out in geometry how that's so again. And that Hilbert, for example, added a postulate of continuity, that for Leibniz was this principle of continuity and principle of perfection, the completeness that is arrived at. And then, of course, this is part of a greater dialectic and what's necessarily a fuller deductive account to be able to have superclassical reasoning that is never a phenomenological matter of discrete finite things and counting fingers, which is as the abacus we might describe, or otherwise as a means of the finite means, has its limits, and that the limitless has where it is to attain to. So everything from this fundamental question of metaphysics very simply, and then arriving at an axiomalist geometry so simply, and then having that to make for Euclid's geometry and as well a point at infinity, all these matters of perspective and projection for that geometry is motion, these sorts of superclassical concepts that are available to be formally and rigorously book kept as part of the object sense, so that all our theories that have to do with logicist positivism and the phenomenological and requiring it to be observable, these sorts of things remain so. Has that by equipping thusly the mathematical models and the mental models and the models of semantics, what would be these metaphysics, as being plain physics and plainly ontological, helps to effect to relay that this way it can take a great many of what are the perceived deficiencies of logicist positivism, never being complete, never being true, never really saying anything, and having no ontological status per se, except as just this very transient sort of vacillation about it. That instead, in the greater surrounds, the theory overall, that for this logos, this discourse, and for it can be appreciated to be expected as a combination of part of the gift of mental faculty that is for all sorts of thinking beings, and so on. So thusly, it's arrived at to revisit the classical accounts of the superclassical to help to explain pretty much for Zeno's arguments to start why it is so, that it's arrived at the deductive inference is how these things are arrived at, that either way the inductive impasses are readily given to take any theory that doesn't have these greater accounts and just show how it's missing, that it's merely a fragment at best, and that it's wrong, and given the same form, an argument in the same form that has opposite conclusion. That this has that there really is a strong account why there is an axiomalist natural deduction and an axiomalist geometry to arrive at what is to be inferred, to be thought of, to be made rational and as of the reasonable, that the rational and reasonable are the same thing yet, see? And then it arrives at all these, these great accounts of geometry and numbers, and for the theories of arithmetic and algebra and analysis, and for number theory and topology, mathematics, so that there is the logic, and it's a modal relevance logic, and it's classical in many ways, and it excludes some of what are perceived as the vagaries as after material implication. Basically establishing that Chrysippus's moods make for the modal in effect, so that deductive inference can be kept safe and sound from otherwise ex fossum quod libe, and Plotinus's plots, as it were, so that Aristotle won't be made a liar, and if someone else is with his arguments, he can show them how to repair those. So with that said, here's a little book on function theory, the theory of functions. And so function theory has that, it's one of the more flexible or fluid definitions over time in the descriptive definitional dynamics of mathematics. So once it was just figured that after an analytical setting is established at all, and you have dependent and independent variables, that then for a function relating, usually for the domain and range, and then we have a language that grew to expand the idea of the image as either left-hand side and right-hand side, that most always and usually in these matters of relation, there's a sort of left-hand side and right-hand side, or the LHS and RHS. And so then as with regards to those being made first class themselves and just considered what they are as what they relate to each other, that relations as defined in matters of equivalence classes, usually as after logic quite directly, that relations and equivalence classes then make for functions, and then for the parameters and arguments and the variables as they are, what makes to arrive at for function theory, these types of things. And then as with regards to function theory, then functions and functionals are made their own sorts of first-class objects. As with regards then to operators over then, that the operator calculus gets working on functions. So that we start working in mathematics in expressions like derivatives and integrals, and then that they are as well considered to be that after the application of the operation, it results in an object the same kind of type of thing. It's a function. And so a derivative of a function is a function, yet as well that it reduces sort of to a constant. It's the inner product at the edge of this, whereas the integral of an integral is a function. It's indefinite. And then with regards to taking the definity of it, the definitiveness of it, definity not really being a word, but definitiveness of it, that is established for what inputs so parameterize it. So function is changed from the definition of what they then for a while called classical function, which is that, well, classical function has no vertical lines. And so when you draw something like a circle in its parametric form as x squared plus y squared equals 1, or any number of squares, their sum equals 1, or the radius, say, that makes for an example of something that has a parametric form. It's by a formula. And then as with regards to a function, it's broken down into piecewise functions. From an analytical setting, usually called a Cartesian basis, or after Cartesian coordinates. And then otherwise after a coordinated setting, that the ordinates and abscissa make for then like these subnormals and subtangents for the normals and tangents of the line, that for any given curve in any given coordinate setting, that there's a tangent is incident to the curve, but it's a straight line incident to any curve, and that the normal is perpendicular to the curve at any point. It's a straight line as well. And so the idea is then that the curves have their instantaneous rates of change and their infinitesimal regions of integration or integrable areas, regions or areas in the areal, for the area and the volumetric, has then as a great part of analysis what can be made of functions, what they describe between the functions, their graphs or charts, and the coordinate axes of the coordinate setting or the Cartesian. So everybody knows that as x and y in the xy plane, and that those are tuples of real values, the coordinates. And then there's also polar coordinates directly introduced that have to help relay that vis-a-vis a linear basis for vector spaces and linear algebra, what's to so follow as a great means of getting things fungible and as well tractable. Then there's also, after the polar coordinates and such notions of the spherical coordinates, or otherwise what there are to make of these systems of numbers that are as well geometrical in the setting of these points and spaces in the local and the global and all these kinds of things. So So functions then are often considered as just these parametric forms that have graphs and charts in the real space of these things. R squared is the xy plane. R cubed is x, y, and z. Oftentimes it'll be indicated as like, well, on a plane we have x and y, and then where's z? It's like we have also the right-hand rule that then by following from one direction to the next, then the orthogonality and the direction of which is positive and which is negative in this third dimension is according to just like, given that we have a fundamental asymmetry of left and right, which is its own kind of thing to figure out. Up and down seems so clear, but what about left and right? That it's the right hand rule is a thing, and then that makes for the inner and outer products, and then usual direct products, and then also things like the cross product is with regards to whether the results are smaller and scalar, or outer and multiply vector, or as with regards to in the same space, or if the same space is after a particular orientation, say, that the theory of functions, furthermore, has these matters of definition going on. So the classical functions, it used to be, it's just like if you can put a pencil to paper and draw it, then it's a function that defines it somehow, because you can relate it to like a sweep around, and then over the times and courses of that, where it is in some other coordinate setting. So there is a way to define as a function over a space for a projection and perspective any kind of put in pencil to paper, move the pencil and lift the pencil, and any kind of trace a chart would have a parametric form as some kind of formula or function. But then it got to where the functions were, the classical functions were considered that they have no vertical lines, because that would be infinity. To take the derivative and find the tangent line, then that tangent line to that curve would be a vertical line, and the every line that's not a vertical line has a finite slope with regards to rise over run in the usual coordinate setting. So if it's not finite, then it's no longer a number. It's not a number in its usual accounts, and so what's to be made of it is like nothing. It's not a function anymore. And so then to get into where then that was changed a little bit, and over time we have functions today, and we have real functions that have like, they don't include infinity, and furthermore they can't really have iota values, which here are the as if the infinitely divided with constant monotone strictly increasing differences, the differential, plainly, to arrive at one of these other models of real numbers. Because our standard linear model of real numbers is after the rationals and like all the ratios, then fill in the gaps in that and call them that the real numbers, because it's shown that there are irrational and transcendental numbers. And so the complete ordered field is a model of the real numbers, and it's built like in set theory and our usual candidates for foundations. But then these line reals are just another one, and it's ancient, of course, as well. It's matters of the continuous course of passage of time as of an infinitesimal increment. It's yet constant and strictly monotone increasing. And then there's these signal reals, each of which is a different structure in terms of, say, a set and all these relations and the functions that exist among them, and that make it so that like not all functions are Cartesian vis-a-vis whether these functions are real. Then there's with regards to the real values that they have and matters of discreteness and continuity, which just aren't defined usually in the standard way. They're just, it's like, what's the definition of a continuity, a continuous domain in modern mathematics today? It's like, well, we don't have one. We have kind of Dedekind completeness is what it's called. It's after Eudoxus and Eudoxus completeness, and that's after Cauchy, and then for Weierstrass, that's what they arrived at, what they needed, and it makes a good account for delta epsilonics, and it's great and perfect because we just use the laws of arithmetic of real numbers as they're given. And there's trichotomy, and there's what's called extent, density, completeness, and measure. This extent is finite or infinite. The density means that in any particular region there are infinitely many. And the completeness means that there's the least upper bound property is established for all. And then measure has the existence of sigma algebras, so that when you take it apart and put it back together, it adds up to the same. So that's continuity is as it's briefly defined. And there are at least these three models of continuous domains: line reals, field reals, these standard ones. So line reals are just iota values or infinitesimals between 0 and 1 only. And then field reals are like between negative infinity and infinity. Instead of just between 0 and 1 running out the integers, it's between negative infinity and infinity running out the integers. That leaves the rationals. And then it's just defined that it fills in the rest of the gaps with numbers like pi and otherwise algebraic numbers, and then the rest of the transcendental numbers, these irrational numbers. And then the signal continuity is like, well, when you have like a given bounded region, and then you have a particularly dense organization like the rationals, and so if you had twice that much, then it would be like Shannon and Nyquist's theorem from information theory for the perfect reconstruction of signal sampling that makes to arrive at another continuous domain according to extent, density, completeness, and measure, those being the requirements and sufficing for being continuous domains. So thusly, we can make it so that instead of kind of having been stuck without otherwise these aspects of simply superclassical reasoning, because these aren't extendedly very different, and they each have their own means of building them in bounds as limits of real functions, that then the result in the real is like is just right beyond there what would be a real function that is not a real function, that then it lives in axiomatic descriptive set theory as of a sort of formally rigorous, valid and sound thing that otherwise is built on all these different courses, like for the line integral or in the completely metrizing ultrafilters, that would just contradict each other if they didn't have it fixed right from the get-go. So thusly, it's equipping the foundations of mathematics with these objects that are continuity and continuous domains for an infinity as simply as it can be, and just like as we've been reading from like Leibniz and Hilbert and Husserl, all these great minds about it, that even though many accounts have that it can never be so, and it's a classic theme that is it's classicality of a sort, that that's just not enough, and it's reached the point where it's showing its cracks, as it were, and ends up contradicting itself when other perfectly suitable means and methods make for such objects as real, and it causes hypocrisy, and then it makes everybody kind of well, how you might say, people who, not everybody necessarily, but people who find these things to be incommensurable or inconsistent, that it makes for a great schism, and it can't be so, and it violates the conscientiousness of logicians and mathematicians. So by putting it together these sorts of ways, like, well, and it's after an axiomless natural deduction, thus after an axiomless geometry, because otherwise some of these things are fixed all the way back in the definition of numbers and geometry. So giving that in, and then for something like set theory, a theory of one relation, to have this extraordinary bit, because it's like it's Kant sublime, it's extraordinary, it's in the noumenon, indeed it's so, yet it's just right there for the phenomenon to keep itself together. That if it weren't for these things, then it's possible to have that mathematics is at best incomplete, and it's not a foundations until it has all these things either. And then physics, of course, needs all these things too, because it's a part of continuum mechanics. And there are multiple laws, these three different continuous domains, then in their doubling and halving spaces, which are shown to exist. Without having all those together, then all these things end up just having like random fixes all up in the theory, and that's not. It's practical sometimes, And it's empirically so. I mean, they have those numbers there because they add up to what result. But it's not it's not the thoroughly unified theory that it would purport itself to be. And the more it gets complicated and so estranged that way, and cryptological in a sense, that the farther it is removed from what it's simple to relay is otherwise just kind of like, well, we have these superclassical aspects of our theory from the beginning, and then they can be relayed, and then it's become so simple to have it so that instead of eventually having a theory that tears itself apart, there's one that's resistant meddling and keeps putting itself back together. So the theory of functions over time has changed. And let's see what we have with regards to some of these descriptions. So it's largely geometric by means of linear functions. One of the notions of these iota values is that it's not a Cartesian function what establishes it. So it's not a real function, it's not a Cartesian function. It ends up having values that are not members of the complete ordered field. And that's fine, because then it helps express to reflect that they're just theorems about functions, and theories like axiomatic set theories account for a descriptive set theory, a descriptive geometry, and descriptive number theory, that these things are like so. Keeping in mind that set theory is just a theory of one relation, and so it's fundamental in that sense, that all these other kinds of theories are their own theories within this domain of discourse, within this universe of the mathematical objects. So getting back to the beginning of this little book, and it's a brief volume from Dover Publications, a reprint of Konrad Knopp's, Knopp's, Elements of the Theory of Functions, translated by Frederick Bogomil. And it says it's a well-known book of general function theory, and then it's about complex variables for undergraduates, and it requires knowing the foundations of real analysis and of the elements of analytic geometry. So the various sections include 4-5 sections, and they describe the complex numbers and their geometric representations. So here, when we looked at complex numbers back in descriptive differential dynamics, it was discovered that they have at least two ways to define division. And so the one that's usually given is kind of like a principal branch of a singularity of a multiplicity theory. So by having the identity dimension and positive numbers all in quadrant one, then it can kind of have complex left and complex right in these other quadrants, making like it's these dual complex numbers, or the complex diagram, as I put it. So this is just something that goes to show that when you get to define, he gets to defining out what these complex numbers might be, and as by their definition of defining division, then there's another way to do it. And so that was long ago left behind, but it makes it so that it looks like the ordered field, that the complex numbers and the real numbers are isomorphic, or the real numbers as the complete ordered field is unique up to isomorphism. Has that as kind of so, but it has again that these complex numbers have other products. And then there as well as so that you can equip via not quite a real function, but via a limit of functions, -1 to 1 with field operations, that it makes another complete model of a complete order field. So these fundamentally considered uniqueness results or distinctness results about the objects of the algebra. And so it's kind of a superclassical algebra account to be taken into account. That then when we get to stuff like, I've been reading Tinkam's group theory about quantum mechanics, and he gets in all these things about symmetry groups, and then he gets in these like ones that are like, well, these are the ones that just kind of they kind of reciprocate, and so like their inverses might fall out of the group and something like that, and they're totally different vis-a-vis all the parts where they come together and this kind of thing. That he says that this will be the complex numbers and their geometric representation. This is the foundations of them. So we'd say it's kind of a plank vis-a-vis foundations is overall, because it's just the fundamental definitions. So we just say this is definitions usually. The system of the complex numbers in the Gaussian plane. So often we might refer the Argand or Wessel plane. The Riemann sphere of numbers, linear functions and circular transformations is section 2. So this is matters of perspective and transform and projection, sets and sequences, power series. And the power series is a cool thing. That's like an infinitary expression. So all these infinitary expressions are of great and profound value, and they have a lot going on, and they're not all according necessarily to like arithmetic progression, Sumerian conjectures. They're not just theorems anymore. Some of number theory's infinitary conjectures are broken open as independent because there are multiple laws of large numbers, and they're decided variously. Like, will a program halt? It's like, well, maybe the probability is 0.01, maybe it's 0.99, almost any or almost none. Or maybe it's 0.50. Gregory Chaitin, it arrives at 0.85. It's almost like it's a statistical analysis, and like it's just kind of according to statistics, it's arrived at this number. And there are other limit theorems in the central limit theorem, and there are other laws of large numbers in statistics and probability. So Ramsey theory is, again, providing all these kinds of things that make for that it's distinctness results beyond uniqueness results, and it's mathematically a thing. Analytic functions and conformal mapping. That makes for the analytic functions is analyticity, and so when a function like that looks like it's for real numbers behaves the same for complex numbers. And so then people expect to be able to take those as kind of taking point A to point B. Analyticity is, and then with regards to conformal mapping, it's like furthermore the stuff around that is like so. When we looked at Kodaira and Zariski and Lescop's, and with regards to the ideas of topological surgery and the piecewise, according to the pieces of it, taking that apart and being able to put it back together, because analyticity fails on some of these things. They have variously discontinuities or asymptotes and these kinds of things. That this gets into the reasons what make for where it is, how it is so. A nice smooth surface of these things, continuous. The elementary functions, as with regards to powers and roots, exponential, trigonometric, and hyperbolic functions, the logarithmic, the cyclometric functions, and the binomial series. I want to look into cyclometric functions just to recall if I don't know what they are. Sets and sequences, analytic functions. So this is really, this outlook on function theory is mostly about the course of complex analysis. And then otherwise is with regards to elementary functions and analysis. So this doesn't necessarily have so much then about functions, which is kind of like just a series of ordered pairs, say, or a mapping of tuples, or a subset of the elements of the Cartesian product of all possible combinations. Then that some functions are not Cartesian. It's like, well, what's in the Cartesian product of these two domains? It's like it's only the diagonal. Because the way that's tenuously built is this limit of real functions is not a real function. The equivalency function is not a Cartesian function. And so then that solves all these problems otherwise that would arrive directly and keeps it all one theory. But I'd like to look at the cyclometric functions. Page 130. It's like the other day I was looking for page 995 and I only got to 795 and I was kind of confused. I was like, what was I looking for again? Maybe I'll find that again. But that was about something to do with the hypergeometric functions and various elementary functions. So it talks about the logarithm. So the logarithm is a great thing because it's the orders of magnitude of things. So like the orders of decimal magnitude are like how many powers of 10 is like how many places does it have as a number in decimal? It's 100. It's log 100 is 2, but every number between 100 and 999 is 2 point something. That was log. And so the old way that they have a calculator for these using addition formula then for powers and terms was to have the slide rule. And it's this coolest little thing because all it is a couple of rulers together. And they just have a little jig, and so according to this flange, they just slide back and forth. But then on the one of them, it's like it's just kind of like in a linear, and they're modular, meaning they're equidense and equidistributed. And the other one is according to this logarithmic scale. And so you can just kind of slide it and then mark where it is and then add two numbers just by adding these two numbers on the log scale, and then you get back out of it. You can read out of it just by the configuration according to these log linear scales, big sums. And so Even in the like 1950s and 1960s, before there were hand calculators that could add up that many numbers, because it wasn't only like in living memory of most people that there was no such thing as a calculator. There was no such thing as a computer. There was definitely no such thing as a giant monolith of an information apparatus that has the way to find sums. Everybody knew how to do sums, and then also scientists of all sorts and practical engineers, and everybody who had to do sums used slide rules. And so after the compass and edge, which everybody should have manual experience with, not just like seeing a picture or a video of a compass and edge, but on pencil and paper, working out the theorems and making for their matters of perspective and projection. The reading is fundamental, and geometry, its practice in classical constructions is a manual activity. It involves those tools. But then later having access to a slide rule, which is when I was in school, is like, no, we don't use slide rules anymore. And furthermore, there's no calculators either. And so you do everything in pencil and paper. And so that was what we did. And then later, right at the end of when I was in school, they started handing out calculators. And they're like, give us money for these calculators. I'm like, I'm not buying a calculator. It's beyond my limited means as a jobless student, you know. How am I supposed to come up with this $40 for this TI-99? That these days, the students are like, here, buy this laptop and this great thing, and it's like, pencil and paper and school supplies were a much simpler thing, and they still should be, because if you don't have reading and writing, as accords to like being able to the practice of that. I mean, don't get me wrong. I'm not saying that everybody should take penmanship classes until like their handwriting looks the same, and I'm not saying that they should like write out all their times tables all these many times till they've filled the book and all these workbooks full of all the work, vis-a-vis, tapping on the screen and doing exercises, which is a way to do these things. It just has that some of the experiences with things like classical constructions of geometry must be the classical way, and they cannot be learned by observation. They're learned by doing. It's not just a matter of graphical learning, it's a matter of experience. And it's something that without that, then there's not retention, there's not comprehension, and it ends up then there won't be anybody to be able to carry on from these things. So I'll leave off at that for a minute. It's just kind of a thing. So the logarithm, and then getting into like the intuition of the logarithm, is another thing about the orders of magnitude and knowing binary and decimal first, and then about the natural logarithm, and then the logarithm in binary is like LG sometimes it's written. So log is always means log 10 usually, but then ln means log natural, and so it's log in base e. And so this is a great constant because like 1 plus 1 over x, take the product infinitely many times to the power of infinity, equals e. Or it solves for continuously compounded interest, or otherwise that next to pi, that e for Euler's constant, but it could be called Napier's constant, although Napier never really had the natural logarithm figured out. That has probably existed a long time already. So from whenever like the natural logarithm constant was actually first figured out, and it's a transcendental number, then the idea that this 2.728 or whatever it is, and I hope you'll forgive me if I don't have that exactly accurate, that it has a symbolic value, that Euler's constant, or E, is the base of the natural logarithm. And then with regards to pi and E and phi, the golden ratio, then that gets into a lot of different things. And finding relations among those especially is a very important exercise in the practice of all these things. And so it's effective to reflect here in terms of his complex numbers, and then he just has that, he talks about taking the principal value of that among all the multiplicitous values. And so I want to see just what it says the cyclometric functions are. And he gives some identities for logs and power rules and addition formula and like log z1 z2 equals log z1 plus log z2. Log z1 over z2 equals log z1 minus log z2. These addition formulas make for then you can find wherever you find this or that or the other one, you can take the log of it and replace it with this expansion. Or take the expansion you found and replace it with this contraction. And they're the same value. These identities and formulas are the bread and butter of any kind of algebraic derivation. Making for a power series and expanding what would make it the Taylor expansions. And as for the Maclaurin and Clairaut and Taylor and Fourier, those kind of great accounts of power series and when the powers increases in each of the elements of the series, or when the term is according to different coefficients and it bounds in the periodic functions. So where's the cyclometric functions? On the basis of the results, we can undertake to find the inverses of the trigonometric functions. Just as in the preceding paragraph, we consider the inverse of the exponential function. This leads to the cyclometric or inverse trigonometric functions. So these would be familiar as cosecant and a secant. So the cosines inverse is secant and sines inverse is cosecant. And he describes how that's to be made so in the analytical setting, which is of the complex analytical setting. And he talks about the principal values of the function and determining all of the values, the subsidiary values, or non-principal or subsidiary values. So the equation sine w equals z is synonymous with the equation e to the I omega equals iz plus root 1 minus e squared. So this whole idea of after de Moivre's theorem, the whole Euler's identity, e to the I pi, that's its own course. There's been a lot of talk here about the after de Moivre, the Eulerian identity, and then a whole Gaussian bit. This whole course in functional analysis, this book should be titled Complex Function Theory. Has that, it is a way of things. It is not necessarily the way of things. So briefly, let's just see if I could find this definition of complex numbers. It should be at the very beginning about where he defines division. So this is as about, and his author begins his foundations to transfer the problems and methods of real analysis to the case in which all numerical quantities that appear are permitted to be complex numbers. Because then we have a great store of results in power series after Euler's terms in infinite series, which, as mentioned, are these days made open and independent. Their decision, some of these laws of large numbers. Furthermore, we shall carry over the notion of function and its most important properties to the case in which independent and dependent variables are complex, or complex or complex. When combined with the limit concept, this yields the foundations of a differential calculus for functions of a complex variable. It defines a partial accounts, kind of. If we define the two operations, addition and multiplication, and so this was read up from reading from the university texts, and then it says fundamental laws of multiplication. It says fundamental law of division. The inverse of multiplication can, except in one case, always be performed, except for if a and b are numbers, the first of which is not equal to 0, there exists a number x such that ax will b. It says it's quotient. And now it says, he doesn't say where he's going to define division. And he talks about, considers the totality of all conceivable divisions. He's talking about Dedekind cuts and a system of real numbers and points and vectors on the plane. So I'd like to see where he defines division. It does not. All of these laws can be deduced very easily from the most elementary properties of the natural numbers. So he gives that as a fundamental law that division exists. So I'd later go look to these university texts that talk about the complex analysis in the descriptive differential dynamics, where it's addressed that division for complex numbers is an axiom. It's not just derived. It's not just a property of properties and they're expanding the comprehension. It's as well a principal branch and there's more to it. So it's got a multiplicity, an opening, a perestroika, a catastrophe. Does it make for a crisis? In a sense it does, yes. A crisis means that finally it's arrived at, it's like these things are inconsistent. Without continuum mechanics, quantum mechanics, and general relativity point 128 orders of decimal magnitude the wrong way, each other facing apart. There's no gravity in the middle either. It's a crisis in physics. Now you'll often hear it as just like, right again. And oftentimes it's accurate to say that. It's just like, not wrong again would be a better way to put it. Because right is not a thing in science. There's only not wrong, as far as the theory goes, being falsifiable. Yet the popular account doesn't necessarily include the usual kind of rumblings that physics has got a lot of wide open things to figure out still, and it's the ways I think the way to do that is with equipping it from these first principles, the necessary continuum mechanics, because otherwise I can show it quite wrong in mathematics, and so can anybody else. This is the book I've been reading. It's called The Electron Theory of Matter by Owen Willen Richardson. It's from about 1918 or 1920 something. Let's take a look here at this for a moment, because I really enjoyed this book. This guy's a Nobel Prize winner, and he collects together all these different concepts of theory. So it's from Cambridge University Press, 100 Princess Street, all rights reserved, and 1916. So this is the second edition, 1916. So Richardson was the Wheatstone Professor of Physics at King's College London, and he's member of the FRS. And later, at some point in time, he got a Nobel Prize for Physics. And so I just wanted to find some examples of some excerpts where he kind of makes it so that these openings in the theory for where it's bound together very linearly and arrives at something that can, like, according to a configuration of experiment, simplified, an energy of experiment, either extreme or simplified, can arrive at a thing. Then he also makes sure to point out, it's like, also it's got this and that on either side of that arrive at that in the middle that we ignore, but are still always there. So he can't be ignored. Because otherwise you could just kind of ignore this guy with regards to otherwise these things. So he talks about Davian, Berzelius, and Faraday. And so all these different things, people have various kinds of ideas that are outside otherwise the usual count. Maxwell as well has got at least two things going on. On the one hand, it's like Maxwell's super cool. He's got E cross B. He's like, well, the electrical field and the magnetic field, they just cross each other. And it's Maxwell's laws, and everybody adopted that as like the coolest way to describe all this stuff. Because then for Ohm's and Kirchhoff's laws, and whether it's Kirchhoff or whoever came up with Kirchhoff's law, but for active and passive electrical circuits, then it's like we have a perfectly suitable fluid model of electricity, and potential differences like pressure and resistance is like constriction. And so we can have a formula like Ohm's law to compute the resistance, given the resistance of components in a circuit, in a circle, in a network, or is according to like in a parallel or in series, passive electrical devices for Ohm's law, that it works just like a model of fluid. And that's great. That there's all this other stuff going on with it. So Maxwell at least has two things, which regards to which of Maxwell's propositions is real, and which of the other one is kind of derived or virtual or fictitious. And Richardson as well very well affects to describe that when it uses the term fictitious only because it's kind of looking the other way, but really in a convolutional setting they're both quite real. What's called fictitious in these forces. Otherwise, we just call it not a thing in this kind of thing. So he talks about Zeeman. So Zeeman, another Nobel Prize winner, he got it for knocking down Faraday's magnetizing the light bit, as was discussed here before. Sometimes the greatest things that get these things are like simplifications that arrive at more numbers, longer numbers. And then they are good in their limits, in their domain, in their configuration. And then as regards to that being incomplete, is this other kind of thing. So finding new physics is what they say sometimes, or doing physics and that kind of thing, are usually the same thing. But mostly it's bringing other known physics, all these different empirical things into the existing theory, because currently they don't fit. Talks about Lorentz, and so Lorentz, of course, is the great unifier. It's all Laplacians. So then Richardson goes on into this account of like the Laplacian, the Gaussian integral for surfaces instead of volumes, because we can't add them up. To get into these things a little bit more later, and with regards to Green's function and Poisson and that for Lorentz, that's all. Lorentz is like, well, Lorentz, what's your deal there? He's like, I made a Laplacian and set it to 0, and I added a time coordinate into it too. It's like, okay. And then Larmor, because Larmor is coming up after Faraday and Fitzgerald and Heaviside and Maxwell, and he's got like, well, Larmor forces are also here in this somewhere, and so they got going on these things. And he talks about how Thomson and Wiechert have their things going on. Today the account is like, you will learn about a test particle. What is it? Oh, it's a non-thing. It's like an infinitesimal, what would be an electron with an infinitesimal amount of charge. With regards to electricity and mass, the ratio, and then it's kind of given a fixed quantity, and then you're going to compute the sum of all the potentials and show that in a non-adiabatic course that, or rather in an adiabatic course, that it adds up one way, and then you're going to use that to derive Ohm law and then later Kirchhoff law. So for Wiechert and Wiechert, and then as mentioned here in one of these other talks, like some other people today have found other ways to compute these potentials that are their own. They've found their own mathematics to do these. Electrical engineers and people who design electronics, chip designers, you know. He talks about Lorentz and Zeeman and Thomson and Millikan, C.T.R. Wilson, J.J. Thomson, Ronch and Reyes, and then he starts just describing that the beta particles and electron streams made out of stimulated radiation are different than current and electrical current here. That current usually would mean electrical current in this kind of concepts vis-a-vis like the current of a river or a current of water, the liquid model for the fluid model of it, because they have core effect and skin effect, or the opposite, that all the electrical current flows most on the outside, and all the liquid current flows most on the inside, the core effect versus the skin effect. That's the beginning and not the end of their differences. And then keeps talking about the electricity to mass ratio. Is like, well, what is an electron and how much does it weigh? What is its mass? The idea was like, its actual mass is vanishing because it's mostly charge moving. So it's kind of given to be charge moving. It's like, what is it about? So when you hear about like Higgs boson, and the idea is like, well, Higgs gave a theory, and then the Higgs field gives mass. And it's like to mechanical, kinetic, massy elements. And it's like, well, does that have anything to do with this electron theory? Or on the other side, they're saying everything's kind of like electrical. What makes it like so? Is like, well, yeah, no, they are totally at different worlds. So does that make that there's one theory of physics together where it has both? It's like, well, no, you end up having to have such a large piece of graph paper to have both their points plotted on it that doesn't quite shrink to fit the box anymore. So it goes to show though that these different theories are looking at the same elephant from different perspectives, and they're both right from what they can see, but neither of them are complete in what they can't. Experiments by Townsend. Wilson, Townsend, Geiger, and Rutherford. So Geiger and Rutherford help introduce that, like the radionuclear and the electromechanical and electromagnetic and electrical field things, radiation, are different. So what you call radiation usually these days is nuclear radiation, and it means like the deadly fatal ionizing radiation, like all these different machines that make for X-rays and millimeter wave radar and this kind of stuff use. That each have kind of like their lethal dose associated with it. Vis-a-vis electrical field radiation, which is like it's radio, and it's usually considered to not really be bad for things, but you know, if you put live radios in a box of lab rats and nothing in the other one, that the control group swims better and dies less. You know, that there's still not, it's very loud. It's even if it's not something we were particularly tuned to hear, that it's a particularly strong amount of energy involved in these things. And then the light, as we've been describing before, is like its intensity as of the of brightness, and as well with regards to shadow, that these kinds of things make for these various penumbral type of accounts, though that it is, well, at least something that usually for real photons they're visible, vis-a-vis invisible photons and colorless green. That in the course of this talk today, where we'll arrive at then is that in the beginning of reading Richardson's book, it's arrived at that a model of waves is usually a model of propagation and change in an open system of energy, just like in moment and motion as it began. So in this continuing further development, it's taking a deconstructive account of these great giants of the theory. And this theory is still true today. And then its interpretation was all these different approaches to, like, let's unify the corner of supersymmetric field strengths and call it the Higgs boson. It's like, there's all this other stuff going on. Besides the fact that mathematics has to figure all this stuff out underneath, and it can be done, and it's pretty simple. Then to arrive at things like the function theory and that, like the whole analytical course, then of all the derivations that are put in to make analysis, and what it means when there's a deconstructive and reconstructive account that makes this pseudo differential and these other ideas that come together again. And it's quite thoroughly standard in a way, and it's continuous in a way. Warm regards, gentle readers. Thanks for watching this video today, or when you do. And if you actually take the course to follow these videos like a course, I wouldn't be surprised if it would probably be better to already have a pretty heavy mathematics and physics degree first. Yet as well, it should speak to the entire introductory account. That this stuff, these uses the same words all throughout. Warm regards.